Welcome to the summer 2016 installation of the Autonomy Incubator student exit presentations. Jacob Beck is with us from Penn State. This is his second term with us here at NASA Langley, and his focus before and his focus this semester has been on robotics and specifically gripper capabilities. So with that, I'll hand it over to Jacob.
Thank you, Danette. So my focus on research has been, as Danette says, robotic grippers, specifically aerial robotics, grippers we can put on flying vehicles. So this is the quad chart, which you've probably seen many times already by now. Quickly go over some of my approaches, pick out some concepts, design some things. We'll cover this in more depth. So this presentation specifically, our group is trying to increase autonomy of aerial vehicles. And my specific place within that group is to give us the ability to handle packages, sensors, and other devices in the real world. So I have a couple of approaches I've looked to over the past 2 semesters. So we're going to go through those now. First one is a soft pneumatic gripper. Then we have a system that's inspired by spacecraft docking, and then finally what I call the Spiderbot. So first, the soft gripper. The idea behind this is that you have this structure made out of a soft material, typically silicone rubber. It's hollow inside. There's chambers, and when you inflate these chambers, they start to expand, and the entire structure will bend in a way that causes it to grab things. This original idea comes from the Whitesides research group at Harvard, and there's several advantages to this sort of technology. Specifically, since they are soft, they're safe for human interaction, unlike a lot of the typical hard robots that are used in manufacturing. And because they're soft, they can conform to objects that are irregular or not designed or engineered for robot interaction. So this is the design I came up with for my gripper that I wanted to fly. This is an improvement on what I've done here last semester. This is a 4-fingered design. We had a problem in the past where we only used 2 fingers and our targets would slip out the sides. So we added more fingers. We added a texture to the bottom to allow it to grab things more easily. And I put a adjustable mount on the bottom of the quadcopter so that if we can just land on top of objects and it will adjust to the height of various targets. So here is a video of us performing a test flight of this gripper. You can see as it inflates, the claws curl in. Now, our pressure source is actually a small CO2 canister. We can drive the gripper from any sort of working fluid. You could use water, for instance, but we thought that the most compact and lightweight solution would be a CO2 canister, similar to what is found in airsoft guns. There's also a variety of micro air compressors available that might also be suitable for this sort of purpose. So one of the issues we had was the gripper itself is flopping in the downdraft of the props, and even though, like I said, it can conform to various geometries, it still only gives you a relatively small area to place over the target to grab things. And this is something I'll come back to, and we'll talk about that more. So that brings us to the next project I worked on with collaboration of another intern, Nick Woodward. Hi, Nick. We call this the Universal Attachment System, for short UAS, because that clarifies things immensely, right? So the basic idea is we have these 2 components. The one on the left is the receptacle. It goes on the vehicle, and the one on the right is the tetrahedron. It contains a payload. The receptacle is a big cone that the tetrahedron can slide into and lock in place. It has these collars that close around the tetrahedron to lock it down. And it has an integrated IR lock camera that allows us to track to the target. The tetrahedron is designed so that it encloses the payload, and we specifically chose this shape because when you drop it from the vehicle, it could land at any orientation. But no matter how it comes to rest, there is always one of these spheres on the vertex pointing up, and that presents us with a target to grab. So this is showing how the system actually works. It's a bit difficult to explain with words. So the tetrahedron enters the receptacle, and then this actuator closes these collars around the sphere. And this is what actually causes the system to lock down and hold the cargo in place. So here we have it, mounted on the bottom of a quad. A couple of things we had to do with electronics and software to get everything to work. We have a DDS interface to talk to the rest of our control systems. It's very simple. It just listens for arm and disarm messages. The DDS interface communicates over the serial port to the Arduino, which actually handles the very simple logic that drives everything. Once the system is told to arm, it doesn't immediately close, but it is active. There's a bump switch that when the tetrahedron enters the cone will be triggered and then cause the jaws to automatically close. So in this way, it's not the responsibility of the other systems to tell the receptacle when it actually needs to close, but rather you simply prime it and tell it you're ready. So here we have it on a drone and demonstrate it in action. This is a footage cut from our final demo. So now that it's landed on the target, this bump switch has been triggered and it's automatically closed. Now the UAV will return to its destination, bringing the cargo with it. Once it arrives, it receives the disarm message and immediately releases the payload. So that brings us to the last topic, which is what I call the Spiderbot. So we saw earlier with the, specifically with the soft gripper, we had issues with this, but also with the UAS, the previous design. The level of precision we require to actually land on top of our targets and interact with them is extreme. We're talking accuracy on the order of inches. In the real world, we're lucky to get within several feet of our targets. So we started to brainstorm various concepts that would allow us to extend the workspace of a drone once it's landed or from a hover, so that the drone itself isn't required such precision, but instead we have another mechanism that can more accurately track to our targets. And here's some of the ideas I came up with. I thought we could do like a sliding claw, or maybe some sort of walking device, some gripper on a very long arm, or some smaller vehicle that is deployed. Eventually, we chose this walking claw idea, and this developed into the Spiderbot design, of which you see here. Some of the features I designed into this were a winch on the top. This allows it to descend and ascend from the bottom of the UAV. This has an integrated current sensor that allows us to infer the torque. They are tactile force sensors in the feet so that we know when we're in contact with the ground and various targets. Software. So the basic idea behind this is the most complicated part, the inverse kinematics, the solutions for various joint angles that allow us to actually walk, is all solved offline. I wrote a program that will take our leg configuration, pass to it a variety of parameters that define how the robot should walk, and then it'll just brute force it using a gradient descent to find all the solutions. Once we have those solutions, we have the control software, which essentially is just going to read through those and tell the servos where to go. So here's a high-level overview of how the control software for the Spiderbot is structured. It's based on the Python multiprocessing library, which allows you to run each node in a separate process and then have them communicate through pipes. So here on the left, we have a teleop interface or an autonomy controller, which is basically you just set whether I want to drive it by remote or I want it to do things on its own. That stuff sends commands through pipes to a leg and winch controller, which in turn send their commands to the servo controller, which drives all the actuators. So, constructed this prototype. Here it is in all its glory. All the elements we 3D printed in our own lab. Power comes from an external source. There is no integrated battery. Currently, for bench testing, we're using a wall power supply, but the idea is that once we integrate it with a drone, it'll leach off of the drone's main battery. Same idea with computing. We're using an offboard computer, and all the control software will be, again, run on the drone's main control. So here we have it in action. You can see here, this is the basic idea. It's attached to the bottom of a drone. It'll winch down, grab the target, and then winch back up. What you're seeing right now is all remote control, teleoperation that I'm currently doing from my laptop. This part is integrated with Deegan's computer vision software, which we discussed earlier. This is the autonomous setting in where we use feedback from Deegan's tracking algorithms to identify the target and then send the commands to the servos. So the robot will autonomously detect and track to our target and then grab it without any human intervention. You can see once the robot has approached the target, it enters this grab pose. So that's the end of my presentation. I just want to say thank you to everyone here in our group, my mentors, and all of NASA for a great summer. So the question was, which concept is going to have be the most applicable? And I think, well, we've currently successfully tested both the soft gripper and the UAS. The UAS was actually what we used for our a large demo we had a couple weeks ago. So currently that is, I'd say, the most developed system. It's what we're currently using. But I have high hopes that the Spiderbot is going to overcome this issue of precision landing. Of course, there's more work needed, another generation of prototypes for sure. So, but at this stage, I'd say, yeah, it's the UAS, but in the future, I'm hoping for the Spiderbot.
So I'll follow on to that. What work does need to be done? What's your future work? If you were going to be here another month, what would you focus on?
Well, right now the Spiderbot has the ability to ascend and descend from the quad. We have the computer vision integrated, and it can navigate on its own. The one part that we're having difficulty with is actually interacting with the target and grabbing it from the ground. In the video, you saw that if we descend directly over the target, it's easy to do a sort of bear hug around it and pull it back. One of the things we still need to figure out, though, is how we're going to grab it while we're on the ground. Now, it's possible to use just the front legs, sort of in the pose that you saw earlier, where it'll grab it with just those, but it will really depend on the target. Again, this was a huge advantage of the soft gripper, and also with the UAS, the soft gripper can conform to various targets. It doesn't need to have a designed payload. And the UAS is designed to work specifically between those receptacle and tetrahedron, so there's no unknowns there. The Spiderbot may end up needing a sort of equivalent engineered payload to the UAS. It would certainly simplify the controls and design that need to be done for the grabbing. But eventually, of course, we would like to be able to use the Spiderbot to retrieve any type of arbitrary package.
And when it's attached to the UAV, it would be controlled by the UAV, maybe over wireless or a wired connection?
The goal is to have it a wired connection to the UAV. So it's tethered to the UAV, which is providing both power and computation resources to drive and control the robot. In this way, we're not adding more mass than necessary to the UAV. Thank you, everyone.